Section 7 of National Geographic Magazine, Volume 2, Numbers 1 and 2. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. Report: Geography of the Air, Part 2, by General A. W. Greely. During the year 1882, the year of great flood in the lower Mississippi Valley, the outflow at Red River Landing, Louisiana, was 202.7 cubic miles, of which the upper Mississippi River above St. Louis furnished 16%, the Ohio 43%, and the whole Missouri above Omaha 4%. The upper Missouri Valley, that is, from the mouth of the Yellowstone up to the sources, and the middle Missouri Valley, from the mouth of the Platte to the Yellowstone, each furnished only about 2% of the entire amount of the water which passed Red River Landing. The lower Mississippi Valley, including the Arkansas, etc., furnished 32%. During March, April and May, 1882, the time of highest stage of the water of the lower Mississippi, the outflow at Red River Landing and through the Atchafalaya measured 82.7 cubic miles. During this time there flowed through the upper Mississippi River above St. Louis, 14% of the amount; through the Ohio, 38%, and through the Missouri 6%, while the rivers of the lower Mississippi Valley contributed 41%. The water that passed Omaha was 1.92 cubic miles, or 2%, of the flow of the whole Mississippi during the same time. The water which flowed from the upper and middle Missouri valleys during March, April and May, 1882, was for each valley, probably only 1%, of the water that flowed through the lower Mississippi River. The flood of the lower Mississippi was undoubtedly due to the great discharge of the Ohio, supplemented by heavy river inflow below the mouth of the Ohio, and unusually heavy rainfall in the lower Mississippi Valley. The ratios of river outflow to rainfall over the catchment basins, as derived by Professor Russell from the 2 years' observations, 1881 and 1882, were as follows: Upper and Middle Missouri Valleys, about 335,000 square miles, 13%. Lower Missouri Valley, about 210,000 square miles, 12%. Entire Missouri Valley, about 545,000 square miles, nearly 13%. The Upper Mississippi Valley, about 172,000 square miles, 33%. Ohio Valley, about 212,000 square miles, 40%. Lower Mississippi Valley, about 343,000 square miles, about 21%. The above percentages, while showing the averages for 2 entire years, and so of decided value, are not to be depended upon for special years or months. For instance, in the Ohio Valley in 1881, the outflow was 33%, while in 1882 it was 50%, and as the rainfall in 1882 was 180 cubic miles against 151 cubic miles in 1881, it appears evident that a much greater proportional quantity of water reaches the rivers during seasons of heavy rainfalls than when the precipitation is moderate or scanty. Evaporation is also a very potent cause in diminishing river outflow, and as this depends largely on the temperature of the air and the velocity of the wind, any marked deviation of these meteorological elements from the normal must exercise an important influence on the ratio of outflow to rainfall. In connection with Professor Russell's work it is desirable to note that Professor F. E. Neiffer has lately made a report on the Missouri rainfall based on observations for the 10 years ending December, 1887, in which he points out as an interesting coincidence that the average annual discharge of the Missouri River closely corresponds in amount to the rainfall which falls over the state of Missouri. From Professor Neiffer's figures it appears that the discharge of the Missouri River in the 10 years ending 1887, was greatest in 1881 and next greatest in 1882, so that the averages deduced from Professor Russell's report of the outflow of the Missouri are too large, and should be somewhat reduced to conform to the average conditions. In different years the average of the discharge in the outflow of the Missouri varies largely, as is evidenced by the fact reported by Professor Neiffer, that the discharge in 1879 was only 56% of the outflow in 1881. In New South Wales, under the supervision of H. C. Russell, Esquire, Government Astronomer, the question of rainfall and river discharge has also received careful attention, especially in connection with evaporation. The observations at Lake George are important, owing to the shallowness of the lake, particularly at the margin, its considerable surface area, 80 square miles, its moderate elevation, 2,200 feet, and the fact that it is quite surrounded by highlands. Observations of the fluctuations of this lake have been made from 1885 to 1888, inclusive. In the latter year the evaporation was enormous, being 47.7 inches against a rainfall of 23.9 and an in-drainage of 5.3 inches, so that the total loss in depth was 18.5 inches for the year. It appears that the evaporation in different years on this lake varies as much as 50% of the minimum amount. According to Russell, the amount of evaporation depends largely on the state of the soil, going on much faster from a wet surface of the ground than from water. With dry ground the conditions are reversed. In 1887 the outflow from the basin of Lake George, the drainage from which is not subject to loss by long river channels, was only 3.12% of the rainfall. In the Darling River, above Bourke, says Russell, the rainfall is measured by 219 gauges. The average river discharge, deduced from observations covering 7 years, is only 1.45% of the rainfall, and in the wettest year known the discharge amounted only to 2.33% of the rainfall, and has been as low as 0.09% in a very dry year. In the Murray Basin the average discharge relative to the rainfall is estimated to be about 27% from a record of 7 years, and has risen as high as 36% in a flood year. In connection with the regimen of rivers, it appears a proper occasion to again refute the popular opinion that the spring and summer floods of the Missouri and Mississippi valleys result from the melting of the winter snows. This is an erroneous impression which I have combated since 1873, when my duties required a study of the floods of the entire Mississippi catchment basin. It is only within the last 2 years, however, that the meteorological data has been in such condition that the opinion put forth by me could be verified, namely, that the floods of the late spring and early summer owe their origin almost entirely to the heavy rains immediately before and during the flood period. Occasionally a very heavy fall of snow precedes extended general rains, but in this case the snow is lately fallen and is not the winter precipitation. Referring to the Missouri Valley, the section of the country where the winter snowfall has been thought to exercise a dominating influence in floods, it has elsewhere been shown by me that about 1/3 of the annual precipitation falls over that valley during the months of May and June. In either of the months named the average precipitation over the Missouri Valley is greater than the entire average precipitation for the winter months of December, January and February. Wyckoff thinks that the anomalies of temperatures shown in forest regions, particularly in Brazil, with its abnormally low temperatures, are due to heavy forests promoting evaporation, and by causing the prevalence of accompanying fogs thus prevent more intense insolation. He considers this an argument for the maintenance of forests to sustain humidity and distribute rain over adjacent cultivated land, as well as to maintain the fertility of the soil, which diminishes rapidly by washing away of the soil after deforestation. W. Koppen has devised a formula for deriving the true daily temperature from 8 a.m., 2 p.m. and 8 p.m. observations in connection with the minimum temperature, in which the minimum has a variable weight dependent on place and month. The results of Koppen's formula tested on 6 stations in widely different latitudes, indicate that it is of value. Paulsen's discussion of warm winter winds of Greenland is interesting. These unusual storm conditions last 3 or 4 days, or even longer, the temperature being at times from 35 degrees to 40 degrees Fahrenheit above the normal, and they appear principally with winds from northeast to southeast, which Hoffmeyer believes to be Föhn winds. Paulsen contends that the extensive region over which these winds occur make the Föhn theory untenable, and that a more reasonable explanation of these winds is to be found in the course of low areas passing along the coast or over Greenland. This appears evident from the fact that not the easterly winds only but the southerly winds share this high temperature, and that as low areas approach from the west, at first the regions of the Greenland coast within its influence have south to southwest winds. The question of wind pressures and wind velocities is a most important one in these days of great engineering problems, particularly in connection with the stability of bridges and other large structures. Experimental determination of the constants of anemometric formulae have recently been made both in England and this country. From the results obtained in the English experiments it was concluded that the very widely used Robinson anemometer is not as satisfactory and reliable an instrument as a different form of anemometer devised by Mr. Dines. These conclusions, however, are not sustained by the American experiments, which were made by Professor C. F. Marvin, Signal Office, by means of a whirling apparatus, and under the most favorable circumstances, which yielded highly satisfactory results. Professor Marvin has lately made very careful open-air comparisons of anemometers previously tested on the whirling machine, which have shown that, owing in part to the irregular and gusty character of the wind movement in the open air, taken in connection with the effects arising from the moment of inertia of the cups, and the length of the arms of the anemometer, the constants determined by whirling machine methods need slight corrections and alterations to conform to the altered conditions of exposure of the instruments in the open air. This latter problem is now being experimentally studied at the Signal Office, and final results will soon be worked out. Professor Langley has also made very elaborate observations of pressures on plane and other surfaces inclined to the normal, which it is believed will prove important contributions to this question, but the results have not yet been published. It is important in this connection to note experiments made by Cooper on the Frith of Forth Bridge, where a surface of 24 square meters, during a high wind, experienced a maximum pressure of 132 kilograms per square meter, while a surface of 14 square decimeters showed, under similar conditions, 200 kilograms per square meter, by one instrument, and 170 by another. The opinion expressed by Cooper that in general the more surface exposed to the wind, the less the pressure per unit of surface, seems reasonable, and if verified by more elaborate experiments must have an important bearing. There are questions in connection with which even negative results are of an important character, particularly when such results are quite definite, and tend to remove one of many unknown elements from physical problems of an intricate character. In this class may be placed atmospheric electricity, with particular reference to its value in connection with the forecast of coming weather. The Signal Office, through Professor T. C. Mendenhall, a distinguished scientist particularly fitted for work of this character, has been able to carry out a series of observations, which have received from him careful attention, both as to the conditions under which the observations were made and in the elaboration of methods to be followed. Professor Mendenhall also supervised the reduction of these observations, and after careful study presented a full report of the work to the National Academy of Sciences, in whose proceedings this detailed report will appear. Professor Mendenhall says, taking all the facts into consideration, it seems to be proved that the electrical phenomena of the atmosphere are generally local in their character. They do not promise, therefore, to be useful in weather forecasts, although a close distribution of a large number of observers over a comparatively small area would be useful in removing any doubt which may still exist as to this question. It may be added that Professor Mendenhall's conclusions bear out the opinions expressed to the speaker, in a discussion of this question, by Professor Mascart, the distinguished physicist. It has been generally admitted that the aqueous vapor in the atmosphere plays a most important part in bringing about the formation of storms and maintaining their energy. It has been frequently commented on by the forecast officials of the Signal Service, that storms passing over the United States were in general preceded by an increase in moisture, but unfortunately little effort has been made on the part of previous investigators to determine any quantitative relation between the actual humidity and the amount of precipitation or its relation to the storm movement. It has long been regretted that the direct relations of this to other meteorological phenomena were not more fully defined. During the past year Captain James Allen, of the Signal Office, has endeavored to apply the results of his investigations and theories to the practical forecasts of storm conditions. Captain Allen has carefully studied the relations of the potential energy of the surface air, as represented by the total quantity of heat it contained, to the movement of storm centers and the extent of accompanying rain areas. In his first investigations the potential energy per cubic foot was estimated as follows. Supposing the air to have been originally 32 degrees and the moisture in it as water at 32 degrees, the total quantity of heat applied to reduce to the state of observation will be, A equals left parenthesis, T minus 32, right parenthesis, divided by 6, that quantity plus Q, in which A is total heat per unit volume, T is the temperature of the air, Q the total heat of vapor, and the specific heat of air at constant volume being taken as 1/6.168. From Regnault's formula we have Q equals 1091.7 plus 0.305 times left parenthesis T minus 32 right parenthesis. For the mechanical equivalent we have J equals 772 times A. If we divide J by the pressure estimated in pounds per square foot, it will give the height through which the pressure can be lifted if all the heat is spent in work by expanding the air. An approximate expression for the upward velocity, v, may be obtained from Torricelli's theorem, from which we have v squared equals 2 times g times h. H in this case being the height through which the pressure would be lifted if all the heat is spent in work. The theory has been that the storm center will move over that section of the country where V is the greatest, and that the time of occurrence and amount of rain have a relation of conformity to the changes in Q and its actual amount. Auxiliary charts were also made showing for each station the following values of Q. First, highest Q not followed by rain in 24 hours. Second, greatest plus change in Q not followed by rain in 24 hours. Third, lowest value for Q followed by rain in 12 hours. A tentative application of the theory during December, 1889, has given very encouraging results. The problem can be approached in many different ways, but the basis of the solution is the determination of the actual energy of the air, both potential and kinetic, as well as differences of potential. Probably the most important event of the past year to general meteorological students has been the publication of Part 1, Temperature, and Part 2, Moisture, of the Bibliography of Meteorology, under the supervision of the Signal Office, and edited by Mr. O. L. Fassig. The two parts cover 8,500 titles out of a total of about 60,000. This publication renders it now possible for any investigator to review the complete literature of these subjects, not only with a minimum loss of time, but with the advantage of supplementing his own work, without duplication, by the investigations of his predecessors. The publication is a lithographic reproduction of a typewritten copy, the only available method, which leaves much to be desired on the grounds of appearance, space and clearness. The experiments of Crova and Houdail on Mount Ventoux, elevation 1,907 meters, and at Bedouin, 309 meters, are of more than transient interest since they fix the solar constant at a height of 1,907 meters, at about 3 calories, agreeing with the value obtained by Langley on Mount Whitney, California. With this brief allusion to the important phenomena of sun heat, whereon depend not only the subordinate manifestations pertaining to this section, but those relating to all other departments, this report may appropriately close. End of section 7.